Okay, welcome back. Happy Friday. Today is March the 4th. We are going to cover a brand new topic called improper integrals. This is a topic we have not discussed at all. In fact, we're going to talk about this topic for 2 classes, so somewhat important. Coming up, project number 4 is now officially assigned. It is on your table. You had a few classes, actually over a week since the last project was due. I hope you enjoyed that break, because for the next few weeks, it's going to be turn one project in, get a new project in return, all right? So you guys are on the project bus right now. So project 4 is assigned. It is due 1 week from today, which is March 11. So Friday, you could write that on the top if you want, due on Friday. Fair warning about project number 4. For some of you, this is going to be your least favorite project of the semester. For some of you, hopefully it will feel like really good to be doing something a little bit different than your traditional calculation type stuff in projects. This is the project of all the ones in the semester where Caitlin and I are making as much effort as we can to have you guys write some proofs, mathematical proofs, different than mathematical calculations. And so for some of you, this is going to be quite uncomfortable and foreign. We will get you there. There's some video hints that are posted on YouTube and referenced in the project itself, but it's going to be tough, all right? Manageable, but tough. And I say that because I want you guys to start working on it now and not wait until Thursday night or Friday morning of next week, because bad things happen on this project when you do that. You do not have all of the tools at this particular moment to do the whole project, but you got the tools after today's class to do the first several questions, and I encourage you to do what you can now to put you in a good position to be able to tackle those challenging proofs later on when it gets closer to the due date, all right? Okay, so that's project 4, and as usual, you're welcome and encouraged to work with each other and to work with me and folks in the math studio. Lots of resources on this project. Also coming up, let's see, so that's today. On Monday coming up, I'm going to hand you quiz number 4. It again is a take-home quiz, and that take-home quiz will be due on Wednesday. All right, I'll give it to you Monday. You'll give it back to me on Wednesday. Any questions on the calendar? Stunned silence. So I didn't mean it to be intimidating. It was just supposed to be a, hey, fair warning, this is tough, but doable, provided you budget your time and use the available resources, okay? All right. Okay, starting on the top of page 15, here we go. Daily summary. An integral with an infinite interval of integration. Infinite interval of integration. For example, here in number 2, you guys see what we're talking about? What's new in number 2? Infinity is one of those limits, right? So all of a sudden we are integrating over an infinite interval of integration. Or if you have an integral with an infinite discontinuity within the interval of integration, that's a lot of words. Let's take a quick look at, for example, down here. You don't need to go here now, but what's the problem number for x in this denominator? X equals 2 is a real problem, right? Because that's dividing by 0. And hey, that's too bad for us because 2 happens to be someplace in between 1 and 4. So we've got an infinite discontinuity. This function right here blows up at x equals 2, goes up to infinity. Vertical asymptote there. Brand new for us. So if you have either of those two things, either an infinite interval or like a vertical asymptote inside of the interval that you're integrating on, either of those is called an improper integral. Improper integral. In this section, we learn how to deal with such beasts. Please remind me to encourage you to verify answers on the calculator. I might forget. Here we go. Number 1 is misplaced. We're crossing it off. Jumping to number 2. Suppose we want to find the integral from 1 to infinity of 1 over x squared dx. We've got a picture over here. You might add this label to it. That is part of the graph of y equals 1 over x squared. And in part A, it says, what does this integral represent? Well, we know that integrals, or definite integrals, I should say, represent areas, right? Signed areas. This guy starts where? At 1. So I'm going to draw a vertical line here at 1 and ends where? Infinity. So what area are we trying to find? From 1 to infinity. So all of this forever and ever and ever. Any guesses as to what the area is? Remember, area is a numerical thing. Guesses for the area. Infinity is the most reasonable guess I could imagine because it is always positive. Even though it's getting smaller and smaller, it is always positive. And in my mind, if I add positive stuff forever, I'm going to get to infinity, right? It's perfectly reasonable. Okay, so how do we handle this thing here with the infinity? Well, I don't know. Let's change it so that it's not infinity. How about we just change the infinity to a b, a finite number b, okay? I can handle any finite number. So let's try handling this thing with the finite number replacement. So this guy equals integral 1 to the b, 1 over x squared. In order to use our old friend the power rule, we're going to rewrite that as x to a power. So bring it upstairs. And then we do our antiderivative, add 1 to the power, divide by the new power. X to the negative 1 over negative 1, yes? Is this the place where we put the plus c? No, but we do use our good notation, brackets 1 to b. And this means we're just plugging in top and bottom and subtracting. I'm not super comfortable plugging in when I have negative exponents, so I would prefer rewriting this to something that is easier for me to handle. What do you think? Negative 1 over x is easier for me. Okay, so we plug in the top and we just write what we get. Negative 1 over b. That's it. Minus, plug in the bottom, negative 1 over 1. And so when all is said and done, not a whole lot to do here, negative 1 over b plus 1. Okay, so we changed the infinity to a b. Now let's think about the picture again and ask ourselves what this integral, the one with the b in it, represents. So assuming b is some finite number bigger than 1, let's just sort of arbitrarily cut it right there and say that's our b. Then what does the second integral represent? It's from 1 to b, right? That area right there. And we just figured out the formula for that area right there is negative 1 over b plus 1. That's it, right? So we just did like infinitely many area calculations right there. What do you think we're going to do with the b in order to figure out what the real integral from 1 to infinity is? We're going to let b go to infinity in a limit, right? You guys did a lot of stuff with limits last semester, and we know how to take limits. And the way we're going to define the integral from 1 to infinity is just change the infinity to b, and then let b go to infinity. So here is our work. This is the original integral. Leave a tiny bit of space there and copy our integral with the b in it. And then inside of that space, we said we were going to take a limit as b goes to infinity. And the next expression, copy that limit. You're going to be doing that a lot on the homework and also on that project I just handed you. Lots of copying that limit. And we did all of the work for that integral. Let's just put the final answer here. What was it? Negative 1 over b plus 1, right? That was a lot of work inside of that equal sign. Okay, and now we're taking this limit. And as b goes to infinity, I'm just imagining the b right down here is getting bigger and bigger and bigger. And so what happens to this fraction? It approaches 0, right? Negative 1 over some enormous number is very close to 0, approaching 0. So then what's the value of this limit? 1, right? 0 plus 1. Notice I'm not putting the limit anymore. I've already done that substitution. Letting b go to infinity, that first fraction goes to 0. So before we talk about what that really means, again, just a notational thing. I'm going to expect you to do a lot of that kind of writing on the project and on the homework and on our test, which is like forever away right now. But this idea of change the infinity to a letter and then put that limit. And then do all your calculations with that limit in the front. That's what I'm looking for in the project. Okay, what does this one represent in the original? What color? Blue. Apparently, if you let blue go forever, not only is it not infinite in terms of how much area you have, it's pretty darn small, 1. So total area under there of 1. And even if you don't buy it, like if it just still seems like that, you know, that's magic, you know, like it can't possibly be finite. All right, you guys don't believe me necessarily, but you believe the calculator. So let's check on the calculator. So we'll do math 9. So I'm going to do 1 over x squared, comma x, comma, where are we going? From 1 to, okay, I can't type infinity, but I could type, I don't know, 10. That's pretty close to infinity, right? Okay, so if I go to 10, the area is 0.9. Super. Now, how about we try, instead of 10, we'll go, you know, 500, right? Even closer to infinity. Point 998. All right, maybe some of you are starting to get convinced that yes, it is getting bigger every time, right? 0.998 is surely bigger than 0.9. But it's not approaching infinity. This guy's leveling off at 1. And in fact, we shouldn't be surprised when you plug 10 in that you get 0.9, because look, you came up with this formula over here that said negative 1 over b plus 1. If b is 10, it's negative a tenth plus the 1. That's 0.9. Negative 1 over 500 plus the 1. That's the 0.998. We'll do just one more. What did you say? A million. All right. Let's see here. So 1e6. All right. So we'll let that do its thing, and then we'll come back. All right. So I think that's good. Yeah, Ben.
How can you say that equals 0 plus 1 when it's not greater than 0? And you have to say it's approximately 0.
Good question. So Ben is asking here about this limit and changing the negative 1 over b to a 0. And like, is it really okay? And the answer is yes, I really mean the limit equals 0. Embedded inside of that limit is that you are letting this thing go forever to infinity. And we can't actually ever get to infinity. But negative 1 over b gets as close to 0 as anybody could possibly hope for. And you might say something like, okay, I don't believe that negative 1 over b goes to 0. Get me within 0.0001 of 0. And I'll say, no problem, plug in b equals a million. And you say, okay, I changed my mind. That wasn't close enough. I want it to be within 0.00, and you say 47 zeros, and then the number 1. And I'll say, no problem, I'm going to plug in 10 to the 53rd, and it's going to be close enough to 0. And we can play this game for any like little amount of closeness to 0 that you want, any that you name. I can pick a b that's big enough that will get us to within your, what's the like error? What's the tolerance? To within your tolerance. And so we really mean equals. So it's part of the definition of the limit is not that it necessarily gets there for any specific value of b, but that we can play this game. And if we can play this game to your satisfaction and everybody's satisfaction, then we will all say, yeah, equals 0. Good question. Okay. Pretty close to 1. All right. Okay, so down here is our formal definition. If you see an infinity on the top, you change it to a b. Change the infinity to a b and take a limit as b goes to infinity. If you see a negative infinity on the bottom, we're going to change it. It doesn't matter what letter you change it to. I'm just going to change it to an a, and then you take a limit as a goes to negative infinity. This is how we handle either infinity or minus infinity. Number 4, if the limits above exist, we've got a limit here and another one over here, we say the original integral converges. So our first integral converges. It converges to the number 1. Converge means get closer and closer and closer to, right? And so that original integral there, when we change that infinity to a b, our integral got closer and closer and closer to 1. So we say it converges to 1. Yes. Yeah, so if instead it had looked like something like that, then that guy goes to negative infinity, and that diverges. Right? So converges if it's finite, diverges if it's infinite. Okay, let's take a look at number 5. Suppose we want to find this integral. Oh yeah, Trevor.
When we're doing proper integrals, and you
still apply that rule where by negative swap?
Yes. Yeah, so it doesn't make any difference whether the infinity or minus infinity is in the top or bottom. You're welcome to swap them by paying the -1 price that we paid before. Good question. Okay, so what's the problem with this particular interval? Yeah, is that at x equals what number is bad? 1, the integrand is undefined or doesn't exist, right? So let's brush that bad number under the rug by calling it b, right? Let's just change it to a b. As long as it's not 1, I can handle it. So let's handle it if it's a b, and then we'll deal with the problem at the end. Okay, this integral equals integral 0 to b. Okay, 1 minus x. Again, I want to use my friend the power rule. What's the power? -1/2, right? Okay, I'm going to write in here that this is a u substitution. We're not going to show all the details. You can verify them later on if you wish. But this is going to become u to the -1/2. So we'll do our power rule, add 1 to the power. What does it become? To the 1/2, divide by the new power, divide by 1/2. If you want to just make that a ×2, that's a little time saver for us. The u substitution, though, doesn't give us just this. Can anybody see it's a negative? Yeah, I'm going to put this guy in red because that's really the only effect of the u substitution. Again, you can check that later on. Okay, and then this is going to be from 0 to b. Okay, before we plug in the 0 and the b, I really like this to be much friendlier for me because I'm the one that's doing the plugging in. So let's see, I guess we said we were going to change that to a ×2, and I would also change the 1/2 back into a radical. That's just friendlier for me to deal with than that power. So here we go. What does it become? -2 square root 1 minus x. Is that right? And personally, I'm just more comfortable plugging things into that than in the original form. Okay, so we plug in, we're changing the x to a b, so we get -2 square root 1 minus b minus, then we plug in the bottom, the 0. Oftentimes it's tempting to think if you plug in 0, you get 0. That is a dangerous game to play. It's true a lot of the time, but not all the time. So let's be careful. -2 square root of 1 minus 0. -2 square root of 1 minus b, and then plus, I think that just becomes a 2, right? Square root of 1 is 1. So in this case, assuming that plugging 0 in would give you 0 as the answer would have been wrong, right? The answer here is 2, -2. Okay, so we can't go any farther with this. We've just changed the problem, which was a 1 at the top of the integral, into a b. So now it's time to pay the piper and see if we have something we can deal with here. This guy equals, leave a little space, integral from 0 to b, dx over square root 1 minus x. That's just copying the whole thing, but 1 has become a b. What goes in the space? Limit as b approaches 1, right? It's the same technique we used before with the infinity. Just change the problem to a letter and then take a limit. See if it's really a problem. Equals limit as b goes to 0. Notice that gets copied again. Nope, b goes to 1, sorry. Okay, we did a lot of work to calculate that integral. What did we get? It's -2 square root, all that stuff, right? Negative 2 square root 1 minus b plus 2. Okay, and now we take a limit as b goes to 1. And so if we send b to 1, I'm just going to copy everything, but I'm just going to change the b to a 1. Negative 2 square root 1 minus 1 plus 2. Right, that's typically how you find limits. You just try plugging the number in. And in this case, negative 2 square root of 0. No problems at all. Plus 2. Altogether, the answer is 2. Okay, very small technicality here. It's not something I'm worried about in terms of like taking points off on a test. But technically, when we approach 1, we're supposed to be approaching 1 from both sides, both numbers bigger than 1 and numbers less than 1. No, we didn't even worry about that because we just literally plugged 1 in for the b. But if you plug in a number that is a little bigger than 1, right here, what's the problem? You get an imaginary number, right? Because you do 1 minus something bigger than 1, and inside of that radical is negative. So again, small technicality, I'm not super worried about it, but we have a way to say only approach 1 from below, from numbers less than 1. This was something you did very early in your Calc 1 class. Limits from the left, you guys remember that? So don't sweat it. It's okay if you don't include it, but I'm including it, yeah. It does still work. Yes, it's not a problem. I mean, the fact is it's going to be a 0 inside of that radical no matter what, yeah. But this is the calculus of real numbers, and so we're avoiding that technicality by just putting the from the left. Rob?
Decide whether it's diverging or...
Yeah, and as soon as you understand the definitions of converge and diverge, it's a very easy question. Does this converge or diverge? Converges because 2 is finite. I mean, you're either going to get infinity or not. We got not. So this is a convergent integral. We will have, I don't think for any of the integrals that we see, but we will see sequences of numbers that approach 2 different things. We'll call that divergent as well. Okay, so 6 just says we're not going to write the formal definition of what we did, but basically if the integrand has a problem, a place where it's got an infinite discontinuity, just change the problem to a letter and then take a limit. And we're not going to tackle number 7 all the way through, but at least just setting it up. Where's the problem with number 7? Is it 2? The real problem here is that we're actually going to have to do 2 different integrals. Do you see that? Because you can't just approach 2 from the one, like 2 is a problem from both sides of 2. So really what we're going to do is this. We're going to do the integral from 1 to 2 of, I'll be lazy here, that stuff, and then integral from 2 to 4 of that same stuff. That's equal to, right, going from 1 directly to 4. We're going to do a limit now. So first I've split it up at the problem, which is 2, and now we're going to change the 2 up here to change it to a b, and take a limit as b approaches 2. That stuff plus, here the problem is at the bottom, we'll call it a. Limit as a approaches 2. So that's how we'll tackle that. Okay, so not to put more on your plate, although I suppose that's essentially what my job description is. But technically now every new definite integral that you see, you have to be aware that there might be one of these problems lurking. Because if you don't catch the fact that x equals 2 is a problem, and you just do this integral normally without doing any of this limit business, it's very easy to get the wrong answer, but the integral is not, nothing in the integration process is going to say, hey, slow down a minute, you got an infinite discontinuity. You're just going to get a number. And that number could be flat wrong, but there's nothing embedded in the number that's going to warn you that there's a problem. So this is just one more thing for you to just be aware of. Every time we have a definite integral, we just have to take a quick look. Is there a problem? Yeah.
You've got a point that goes up to infinity, right? Isn't there no area under it?
No area under it?
I mean, if it's literally.
Yeah, I think the graph of this guy.
There's no x value. So there's no delta x. But if you get 0.999, 1.9999,
Mhm.
2.0.
I actually think that the graph of this guy is going to look something like this, so don't quote me on it, but I think the graph of this looks something like this.
Well, if you've got one where it's just like a jump that goes to infinity,
Mm-hmm.
and there's no area.
So, I mean, as soon as you have something at infinity, potentially you have infinite amounts of area in there. You guys buy it? It's the same, like.
All right, are you saying that the second part of the graph goes on the left part? No, I'm saying like you got a line,
Mhm.
then on the line at some point there's like a hole, yeah, where y is infinity.
Oh, I see. So at a single value, it's up at infinity. So I don't know how a function would be defined to just be up at infinity at a single value. But generally speaking, if you're infinite at just a single point, no problems, because as you say, there's no area on this kind of razor thin slice. But as soon as you have a tiny bit of width, then right. Okay, I think that is that. Activity starts on the next page. Remember, you're not just doing the technique, but you are thinking carefully about how you write things up. Lots of limits, lots of A's and B's.